You cannot add apples and oranges. In a strange way, this is the reason for vectors, said Professor Gilbert Strang from MIT. Hi, welcome to part 1 of my new video series, Linear Regression, a Linear Algebra Perspective. I had recently created a video series on deriving R squared, and in that series, I had discussed linear algebra. We had found out the best line to represent data or rather the regression line using calculus. In this series, we are again going to discuss linear regression, but we are going to do that using linear algebra. So finding the regression line using linear algebra. Okay, so let's start off. This video will be on the prerequisites, and we're first going to discuss what are vectors. Okay. Now, you may have heard this term before if you've studied maths and physics in school or college. The most common example in physics for vectors is the difference between speed and velocity. So, what they say is that speed only has a magnitude and velocity has magnitude plus direction. And that's what makes it a vector. That it has magnitude in different directions. So we'll discuss that in a more mathematical form today. Now, as I said, a scalar is just a single value, a single numerical value. But vectors, on the other hand, have more than one numerical value to them. So they have components. Let me write that down. Vectors have components. That means that they can have one or more numerical values associated with them. Okay. Now the next main point is that these components cannot be added together. So like I told you earlier, can you add apples and oranges? Can you say that if there are 2 apples and 3 oranges, you have 5 apple oranges or orange apples? It won't really make a lot of sense. So of course some may say that you could, call it fruits, and then you could say 5 fruits and it'll make a lot of sense. But you're changing the label then. Then you're calling it as a collective form. The label changes. Okay. Or, if you take, what if you were talking about things that are much more different from each other? For example, books and apples. Then you can't call them fruits, right? So it's easier to add up the same kind of thing together rather than adding everything together. So okay, that way you keep an understanding of how much is being added in which aspect. Okay, that's kind of what happens even in vectors. Okay, so therefore over here we can say components cannot be added together. Okay, now how do you represent a vector? Let me show that to you. Okay. So let's say you have this vector v, and let's say it has 2 components, v1 and v2. You can write it in this way. This is for 2 components. It could have 3, 4, 5, 100, how many ever components. You would write it continuously in this way. You could just keep putting the rest of the v's under it. Okay. This form of writing the components, is called a column vector. Because if you see, everything is in one column. Okay. Another way of writing it is in this way. Any guesses on what it's called? It's called a row vector because it's one single row. Yeah. Now, the next thing I wanted to show you was this, how a vector looks on a graph. So let me just create a small graph over here. Okay. So sorry. I'm just going to try and straighten this line. Okay. Now let's create another one. Okay. And now let's say, my mistake. Okay. Let me first change it to brush and get it back to blue. Okay. So now let's say V is equal to 4, 2. Okay. Now, one thing to remember is this, that a lot of the times a vector also represents the x and y values. So for example, here you're using a two-dimensional vector. So the first value represents the x value, the second value represents the y value. Okay. This way, let's say 4 comma 2 is somewhere here. What happens is that this vector is in this form. Let me create it with a different color. Okay. So you start from the origin and you create a line till 4 comma 2. And the direction is this. Okay. So therefore it's a vector. Yeah. It's not just a point, it's this direction from 0 comma 0 or the origin. Okay. Okay. Now let's move on to the next thing I wanted to discuss with you, which is vector operations. So let's start off with that. Now the first thing you can see over here that I've written is multiplying scalars with vectors, sorry. Now I haven't talked about multiplying two vectors right over here. I'll talk about it at the end of this slide. The reason is that multiplication of vectors is slightly more complicated. Okay, it's not very straightforward. Okay. Now multiplying scalar. So let's say you have your your vector v1, v2. And now you want to multiply v with this constant scalar c. So this is equal to c times v1, v2. Now what you do is you multiply each component with this constant value c1, cv2. Okay. For example, let's say v is equal to 4, 2. Okay. And now you wanted 5 times v. That would be equal to 20, 10. Okay. Now let me show you the same thing over here. Okay. You'll see this red dot. This red dot symbolizes v, which is 4 comma 2. So it's this sort of a vector. Okay. And over here at the top is 20 comma 10. So what you'll notice is that the distance from 0 has changed. Okay. The magnitude has changed, but the line still stays the same. Okay. In this case, even the direction is the same. It could be so that the direction may be 180 degrees opposite. So if you said minus 5 times v, it would be minus 20, minus 10, going into the third quadrant. In that sort of a case, you're in the opposite direction, but you're still on the same line. Okay. So magnitude may change. Magnitude can change. Unless, of course, you multiply it by 1. Magnitude can change. The line still stays the same. Okay. That's the main thing. Now you could have even multiplied it by half. Then the magnitude would become half. Okay. Now let's move on to the next thing, which is adding two vectors together. This is pretty straightforward. So let's say you had a vector called v with components v1, v2, and you had another vector called w with components w1, w2. Now, when you add v plus v and w, You just have to add the corresponding components together. So this would be equal to V1 plus W1, V2 plus W2. Hence, please do remember that the number of components in V and W have to stay the same. Okay? Even the shape has to stay the same of the vector, or eventually when we learn about matrices, even the matrix. So here, if you notice, let me just tell you one more point over here. This is a 2 cross 1 matrix, or a 2 cross 1 vector, because you have 2 rows and 1 column. Okay? This is also 2 cross 1. Therefore, they can be added together. If it was a 2 cross 2 2 vector, like W was a 2 cross 2 matrix, then you wouldn't be able to add the two together. So the shape, the number of rows and the number of columns have to be the exact same to be able to add two vectors. Okay. And what you'll notice is the shape of the resultant vector is also the same. Yeah. Now let's do an example. Let me just change the color first. Okay. Example 2, 10. So V is equal to 210 plus W is equal to 12, 3 is equal to 14, 13. Okay. So this is V, this is W. Okay. Now let me show it to you on a graph. Over here, you'll see this first blue color line. Second, I'm just trying to find my pen. Okay. This point over here is 2, 12. Sorry, 2, 10. Okay. And this point over here is 12, 3. Okay. These are the two vectors that are getting added. And this red line over here indicates the resultant sum, which is 14, 13. Okay. Now, there are ways to actually picture the addition. If you'd like me to create a video on that, please let me know and I'll do that. It's a very interesting way where you can shift uh, the vectors one by one so that they are all in the same direction and get the sum of the two. Okay. Okay. For now, just have a look at this, the way these three vectors look. Okay. Now we are going to come to a very interesting point, which is linear combinations. What does this mean? So it is said that, let's say you have two vectors V and W. C1 times V plus C2 times W can give you every single vector in the two-dimensional space or the xy plane. Why xy? Because we are assuming that V and W are also two-dimensional vectors. That means they have two components, V1, V2, W1, W2. Okay. Now to understand this, let me tell it to you using an example V and example W. So what if we only had an X component? Okay. So let's say it's C1, X, 0, V, sorry, not V, plus C2, and W only had a Y component. Why? Now if you notice, if you do C1 times 0, it is always going to be 0. So the Y component in this first part is always going to be 0. But using C1 and whatever the X value is here, you can create any X value you want in the entire 2D plane. Yeah. Now, when you do C2 times 0, X component will always stay 0, but C2 times Y can give you any Y you want. And when you add these two together, you can create any combination of X and Y, hence getting all the two-dimensional vectors. Now, it's not necessary that V and W should be x0 and 0y. There are other ways of doing it. There are many vectors of these kinds that you can create. You'll understand this in more detail in the coming videos. Okay. So now Let me also give you a short understanding on multiplication of vectors. Now, if you saw, while adding vectors, all we needed was that the shape of the two vectors had to be the exact same. However, while multiplying vectors, the rules become different. Okay. So now let's say we take the same v and w. V is equal to v1, v2, w is equal to w1, w2. Okay, let me actually rewrite it here. Okay. And this is a 2 cross 1. W is a 2 cross 1 again. Now the reason why VW cannot be multiplied is because multiplication requires you to have these inner two values to be the same. This means the number of columns in the first vector that's being multiplied should be equal to the number of rows in the second. Now, in this sort of a case, what you can do is you can use the transpose of V. What's a transpose? V transpose, I've put a T over here, is just turning the columns into a row. Okay, so in this case, it would be V1, V2. Now have a look at this. What is the shape? 1 cross 2. So this time the number of columns are equal to the number of rows in W. Therefore, you can multiply V transpose W together. Okay. So you could say V transpose W equals, let me actually do this in a different color so that it's more visible. Okay. Let's take orange. Okay. So we can, once again, let me just create a line so that it's easier to decipher. V transpose W is equal to V1, V2 times W1, W2. Okay. Now, how do you multiply these? The method is this. You first multiply the first element of the row vector with the first element of the column vector, which is V1, W1, and you add the next uh, product, which is V2 times W2. Now, the same could be done if there were more components. Yeah. Okay. Now, something you'll notice is that the resultant vector's shape is 1 cross 1, right? It's just one element. And if you notice, the outer values of the two vectors we're multiplying are 1 and 1. Okay. So the resultant matrix or vector has the number of rows in the first vector and the number of columns in the second vector. This is a very important point. In case you would like me to talk in more detail about multiplication of vectors and matrices, we're going to discuss matrices also a little bit in the next slide. Please let me know and I'll create a video on it. Okay, but for now, this much should be enough for the next part. Okay, one more thing. It's not necessary that V transpose W is always equal to W transpose V. Okay, in this sort of a case, it would be, but not for every V and W. When the shapes change, the results also change. Okay, you can give this a thought. Okay. So therefore, just one last point, multiplication of vectors is not like multiplication of scalars because the way you multiply two matrices may change the result completely, the sequence in which you multiply them. Okay. Okay. Now let's move on to the next thing, which is matrices. Okay. So what are matrices? It's very straightforward actually, if you know vector. A matrix or matrices is the plural form and matrix is the singular form. A matrix is just a collection of many vectors, representing many vectors together. So let's say we were representing V and W together, we would write it in this way. V1, V2, W1, W2, for example. And the transpose of this matrix, you convert every column to a row. So the first column is V1, V2, it changes into the first row. First column is W1, W2, second column is W1, W2, it changes into the second row. Okay? Think of it in that way. Now, the reason why we are talking about matrices is because I mainly want to discuss how equations are represented using matrices. Okay. So for example, let's say you have these two equations. 4x plus 2y equals 10. Okay. And the other equation is 3x plus 9y equals 12. Okay. Now, there is one thing over here. So if you notice, these kinds of equations, you may know how to solve them if you've studied algebra. Okay? But our main aim over here is to learn how to represent these as matrices. So let's first try out a simple thing. Okay? We say this is equal to 4x plus 2y, 3x plus 9y equals 10, 12. Make sense? Yeah? LHS equals RHS. Same thing being done as the two equations, but this time we write it in matrix form. Yeah? The right hand side matrix is a vector, a column vector of the two results. The left hand side is a vector of the two equations. Now, let's have a look at one more thing over here. Let me change the color for that so that it's more visible. Okay. Now have a look at this. 4x plus 2y. Does it remind you of something we just saw? Remember the V1 W1 plus V2 W2? Isn't this of the same format? So what if we used 4 and 2 as a row vector and x and y as a column vector? Wouldn't that also work for 3 and 9? Yeah. So hence we can write it as 4, 2, 3, 9 xy equals 10, 12. Okay. Now in the last slide we did not discuss matrices, but it's basically the same thing. You have multiplied this row vector with this column vector. That gives you the first row in the RHS. Okay. You multiply the second row with the same column vector, you get the second row in the RHS or the right hand side. Okay. It's the same thing. We've just represented it differently. The reason for that is also that it helps in solving the equations faster using something called, there are many procedures. One of them is elimination. I won't be discussing it today over here. In case you would like me to discuss it properly, let me know and I'll create another video on that. Okay. But elimination is one way to be able to solve multiple equations using matrices easily. And over here you just see a 2 cross 2 matrix. Okay. 4, 2, 3, 9. But what if you had many more equations? It's very tough to solve. Let's say if you had 50 equations, 50 variables, very tough to solve it manually. Therefore, linear algebra can really help out in those cases. Okay. Okay, so that's what I wanted to tell you about matrices. And now let's move on to the last topic for the video, which is vector spaces. Now, what is a vector space? Let me write it down. Let me write down the definition. Okay. So the definition says that the space Rn consists of all column vectors with n components. So this means that, let me give you an example to help you understand. The R2 space is basically the two-dimensional space or the XY plane. And doesn't the XY plane contain every single vector, every single two-dimensional vector, or every single vector with two components? Yeah. So 2D vectors, right? Similarly, R3 would have every single three-dimensional vector in it. Yeah. That is the main concept behind vector spaces. Now, one may ask that R3 would also have every single two-dimensional vector. Then why are we saying that R2 is the space that has all the two-dimensional vectors or two-component vectors? The reason is, number one, R2 is the smallest space in which you'll have two-dimensional vectors. Okay. Any space bigger than R2 will have all two-dimensional vectors. But R2 is the smallest space that you can find with every single two-component vector. Second thing is this, which you learn about a little later, that a three-dimensional space will have a lot of xy planes. It won't just have one xy plane. Okay, it'll have xy planes at different z values. Therefore, in a later concept, you'll understand that every vector, whenever you add any two vectors in a vector space, their sum should also be a part of the same vector space. Okay, so the sum should also be a part of vector space. That's the that's one of the points we're going to discuss. Now that may not happen if you're talking about planes in three-dimensional space. Okay, that's one more thing. It's called a subspace, a plane that has all vectors, or subspace. We'll talk about that in a lot more detail in the next video. So for now, this is it. I hope you have a great day, and I'll see you in the next video. Bye.